Hello, we're back again with the part 2 of lesson 2. In this part, we want to look at how we can improve our control survey results to meet the criteria. We are trying different options and we see how it's going to reflect in our adjustment or pre-analysis in this case. From what we've known from part 1, so we did the pre-analysis using the UTM coordinates, and then we have to adjust the standard deviation from the pre-analysis for easting and northing of each of those 7 stations. As you can see, if we want to improve the precision of our final coordinates, we're going to have different options. First of all, we can read the distance in 2 ways, like I can read my distance from A to B to B to A, so it's going to be twice. I can also read my angles in face left, face right, and I can do it in 2 rounds, so it's going to double up the reading the angles and double up the reading the distance. If you're doing that, you have 2 options. You can either enter extra distance or angle observation into your data file, or you can go back to the options project, and then in the instrument section you change the instrument precision. If you can remember from the previous section, we had the precision for this distance. It was 2 millimeter plus 3 ppm. So if I'm reading the distance 2 times, so from this formula that we had in the module 1, it's going to be converted to the 1.4 plus 2.1 ppm. So it's basically 2 divided by square root of 2 plus 3 divided by square root of 2 ppm, or part per meters. This one is obviously millimeter and it's plus and minus, which gives you this answer here. You can do the same thing for the angles. Like if I say the sigma for angle, if you kind of remember, it was 4 seconds, so I'm dividing by root square of 2, so it's going to be 3 seconds. What I want you to see is not only the number. Like, look at how, if I'm reading distance, just doing a simple procedure, read the distance twice, you will realize that how your precision is improving, or in this case the number of sigma is reducing from 6.3 to minus 1.2, which is a huge improvement. So these 2 columns here shows that if you're reading distance twice and angle twice, how it's affecting the precision of your points, easting and northing coordinates of the control survey. Again, you can see it has been improved from the first option, and also is improved from the second option. So if I'm reading my distances and angle twice, I'm gonna come with the better accuracy. So if you're doing that, the final result looks like that. This is the plot result. You can see that the accuracy or precision of the position of the point, like this arrow ellipse, has been improved. It's probably not obvious here because it's just showing you the arrow ellipse, but if you think in the software, you can double click on the arrow ellipse and see the semi-minor and semi-major axis for each of them, see the actual number, and you can compare it with the previous one that you have, and then you can see that is reduced. Let's have a look at the software. We need to go to, before I go and change the project option, I will look at one of the relative arrow ellipse, the size of that. Like say this one is 25 mil to 22 mil. Major and minor axis respectively. So I can close, this is from T2 to T5. So please note this number. Then we will go and change the option in the project. I will make it 14 and this one 2.1. It's for 1.4 millimeter plus 2.1 ppm, or part per millions. And then we have angle of 3 because we are reading try, so I'm changing this on 3 seconds. And then I can run the pre-analysis again and go to the network plot. It was 2 to 5, I think. You can see the axis of air ellipse has been reduced by 7 mil roughly each. So there was an improvement in the relative air ellipse. They got smaller. But then again, they get smaller, but geometry strengths and weaknesses of the network is still the same. So let's go back to our slide and move on. Further analysis has to be done in the local grid coordinates, so we have to convert our UTM in this case. In most of cases, your working should be GDA to local grid coordinates, and then analyze the network strengths in detail in that coordinate system. So if you look at the result we've got from the previous data, you will see the adjusted azimuth for T1 to T4 based on the pre-analysis is 90 degrees 7 minutes. So the swing of the local datum to the grid, the UTM coordinate in this case is only 7 minutes, which is not a huge distortion. We can, for pre-analysis stage, we can ignore that. If we make T1 the base station for the local grid with the coordinates of 3000 and 12,000, and then adjust other station based upon that, so we have to subtract this number from easting and northing of those coordinates, then just make sure when you're making up this number, try to avoid to put those numbers very close to the GDA coordinates to avoid confusion. So we try to use the number very far away from what it is in reality. So if someone else having look at your data, they can't be confused that whether it's a local grid or is it actual grid like GDA. So let's have a look at the software this time and see how the data is going to look like. So for this one here, I've already created, but you obviously should go and create it yourself based on what I've explained. So I'm just turning off this one. So if I subtract those numbers from all the stations I've had, then I will come with these numbers here, which is the coordinates for all those points. Two things to remember. First of all, we don't adjust our coordinates for the azimuth swing because this is irrelevant for the pre-analysis stage, and the coordinates of the station, they are just approximation, they are not fixed, and it can be changed. So the other thing is we don't use PSMs in the local grid pre-analysis. The reason for that is PSM are now irrelevant because when the actual survey takes place, the surveyor should read the regress observation to and from PSM 1 and 2 to establish the local grid coordinates and like direction and distance, which basically remove the needs to having the PSMs in the local grid control survey pre-analysis that we have here. Because we already did lots of analysis from PSM1 and PSM2 when we wanted to basically establish our local grid. So we used those PSM as it's shown in the previous steps to get the local grid and direction between, in our case, was from T1 to T4. Once you've done that, then you probably don't need to take consider of them except for as a sighting reference and perhaps emergency recovery for the T1. So if you go and subtract those numbers from the coordinate station you had, you will come with these stations. You can see I fixed the station 1 and the rest are just the numbers that I've subtracted from the previous coordinates. Again, still we are using the 2D pre-analysis. Scale factor, we have to go to the option and make sure that we change this one. I will show you in a sec. We consider the T4 to T1 bearing is fixed and is 90 degrees. See, I have exclamation, which means fixed, but this time I didn't put the question mark, I put the 90 degrees. So this means that I know the exact or true value of the bearing. Then your traverse is going to be starting from T1 backside to T4, and then it's continuing to T2, T3, T4, T5, T6, T7, and back again to T1. You're starting from T1, and then you're going to the loop, come back to T1, and in this case T4, for example, is your backside. And then you have some middle measurement. As we have M, it means that there is a measured distance and bearing from, in this case, T4 to T3 and T1. I'm not quite sure where they are. I'm just showing you we have the angles and two distances for them. That would be it, and as I said, we delete two PSMs. Let's have a look at the software. So these are our coordinates, and we change the traverse observation. So these ones you can see from the slides, but I want to tell you, you have to go to option, make sure that your adjustment is 2D, but you change the coordinate system to local, make sure scale factor is 1. You probably need to make sure that the instrument specification is also correct. Once it's done, you can hit OK, and then we run pre-analysis. So it's been completed. I can have a look at my network. You can see my traverse observation, which wasn't included. The traverse itself was station is at T4, reading from T3 to T1. So this one of the angles and two distances. The other one was at the station T6, reading to T1 and T5. That was another measurement that input that as a separate traverse observation here. Good. So now we've done that, we look at the traverse ellipsoid, and we see how it looks like. You can see the arrow ellipse for T4, it looks like a line. If I'm zooming, I can probably extend this a little bit. The reason for that is the azimuth from T1 to T4. As you can see here, we've held that azimuth fixed to 90 degrees, so there is no azimuth error. All the error is in direction of the distance, so we don't have any northing error, we only have the easting error in this case. So if I want to see the final report of the accuracy, I can go to final print view and have a look at the listing output. Again, the first page is instrument specification and information about the coordinate system. Make sure that it's local and it's 2D. So if you're happy, then you have the fixed station information. In our case was T1, and then you have free station T2 to T7. And then we have number of angles, as you can see, which has been measured based on the coordinates. Again, the standard deviation here has been calculated based on the standard specification of our instrument. Same thing for the distances, and then the azimuth for T4 to T1 is been fixed to 270. And then we have the adjusted azimuth and distance, as you can see here. So because we fixed T1 to T4 to 90 degree, sorry, that one was T4 to T1. That's why the azimuth was 180 difference, because it's T1 to T4 is 90, so T4 to T1 is going to be 270. As you can see, the adjusted azimuth hasn't changed because we've held that fixed. So there is no error for azimuth from T1 to T4. That's why the error ellipse looks like a line. And then we have all distances and everything for all the rest. So I'm showing you more analysis on the slide. So let's go back to the slide and move on. We've seen that if you run the pre-analysis and look at the error ellipse or the observation, error ellipse is pretty much similar to what you've had before. So there is no improvement in this case. And still, station T7 is still relatively poor fix because the larger error ellipse is from T7. So the critical thing is now to realize the baseline have to meet the project requirement. So before we can proceed to other station, make sure that is basically meeting the requirement for the bridge construction. If you kind of remember from the first slide I've shown you, the requirement for bridge control line was plus minus 2 millimeter plus 2.5 ppm at 95% confidence level. If you look at the results from the pre-analysis of the local grid, you can see the distance precision at 95% confidence level is 13.5 plus 7 ppm. So it should be 13.5 millimeter at 95% confidence level, which still is quite high and is way above what it should be based on the requirement. Now, what is our option? How we can improve it, how we can meet the project requirements. First, we have the option to use the better distance measuring equipment, maybe better than total station, or either you can increase the number of observation as I mentioned in the previous section, that you can read the distance like twice or double up the number of the reading the angles. In this case, you can also improve the precision of the measurement as well as the coordinates. Let's look at the option A. So if we want to purchase a more precise total station, we have to spend lots of money. Or another option is we use the GNSS equipment. As we look at the GPS specification or GNSS specification for both the station, we know we have the clear sky. Option A is limited unless we hire or purchase a more precise total station, that in this case we have to pay lots of money or use the GNSS equipment. Examining the GNSS option, we know that both stations have clear sky view, so we can use it for this project. Imagine that we have the distance between T1 to T4, it's roughly 1.9 kilometer, and the specification from GNSS gives us this accuracy for the distance measurement. If you put this number in here, which is plus or minus 3 millimeter plus 1 ppm times 1926, good, it gives you roughly plus or minus 4.9 millimeter, which is at 68% confidence level. If you want to get 95%, obviously you double up this number or times 1.96, which is roughly 2. So it's plus or minus 9.7 millimeter at confidence level of 95%. So you can see, even if you use GNSS, still you're not able to meet the requirement for that bridge control line. You'll have the option either use the longer observation period to improve the accuracy of the GNSS measurement, but still will improve the whole thing marginally, and it's not a huge improvement. You might ask, so what's our second option? Our second option is probably what we are looking at. Really, we want to show you that if you increase the number of independent observation, you might end up having the better accuracy for the final results of least square adjustment in this case. So let's have a look and see. We know this formula, so mean of the standard deviation can be standard deviation of observation divided by root square of number of observations. So if I'm reading the distance 2 times, this n should be 2. If I'm reading 3 times, this one becomes 3, and so on. So let's consider different scenario. The first scenario is if I'm reading the distance forward and backward for T1 to T4, see whether I can improve the accuracy that I can achieve for that control line of the bridge. So if you do that and you put everything in the formula we've had mentioned that a couple of times during this lesson, then the last result would be plus or minus 5 millimeter at 68% in confidence level, which is equal to plus or minus 11 millimeter at 95% confidence level. Still, we can't meet the criteria. So let's increase it by 4 independent distance. Then you can see that the precision will be improved to plus or minus 3.9 and plus or minus 7.6 at 95% confidence level. Your contract expectation for the baseline is plus or minus 1 plus 1 ppm, so it's 1 millimeter, which is going to be 2 millimeter plus 2 ppm at 95% confidence level. So if you put that number here, so if I want to see what's my requirement, so it's going to be plus or minus and this 2 ppm. If you put your distance in this formula, the accuracy you need to achieve to meet the requirement for the project is going to be 6 millimeter at 95% confidence level. Can we meet the criteria? No. Why is not? Because these both number 5.5 and 7.6, they are higher than 6 millimeter. It means that we couldn't meet the project requirement. So we have to bring our precision higher to get in order to be able to meet the requirement for the bridge construction in this case. Let's see what we can do. So now I know if I increase my independent observations, I can improve the final precision that I can achieve. So an approach we are using here is, if we imagine we have to get in order to be able to meet the criteria, we have to measure 12 distance observations, 6 from each side, so from T1 to T4 6 times and from T4 to T1 6 times. If you are doing that, your systematic error will be minimized and the precision will be increased to plus or minus 2 millimeter at 68% confidence level, which is equal to plus or minus 4 millimeter at 95% confidence level. In this case, we could meet the criteria for the bridge control line. Now, the other improvement option is to read at least 2 sets of angle at each station, and also backward and forward distance at each station. So it's not only for T1, T4. So we're going to increase the precision of the observation overall. And then if you combine those two actions and then adjust your angle, if you combine these two, as we've seen, you're going to come with this number. So this is basically come from the fact that I had initially our instrument specification was 2 millimeter plus 3 ppm. So if I divide it by, if I'm doing twice, backward and forward, I have to divide it by root square of 2, which gives me roughly 1.5 millimeter plus 2.1. And then you can also add this line in your data file. What this line means is you will tell the software that there is a measured distance between T1 and T4, which its value needs to be determined with a standard deviation of 2.2 millimeters. So now if you look at our data file, it should look like this. As you can see, I've considered extra line, which is T1 to T4, and I say the value is unknown, obviously. but I want to measure distance until I get 2.2 millimeter precision, and then I will go to option and I make sure that I change the instrument requirement or specification to the one I've just calculated. Obviously, same thing for the angle, because I've measured the angle twice, so it's going to come to 3 seconds of R. Now if you run the pre-analysis and look at the network plot, you see that the precision is increased and we have the better even relative error ellipse than we used to have. Let's have a look at the listing output. This is the adjusted azimuth and horizontal distances, as you can see, and the relative standard deviation at 95% confidence level. Now if I'm checking line T1 to T4, you can see that the distance accuracy has better accuracy as compared to the previous one, and is 4.7 millimeter plus 2 ppm, which is exactly what we want. Let's have a look at the output result. This shows you the standard deviation of the observation as per the specification of the instrument. Again, and T1 to T4 is entered twice, once explicitly as per the notes above, and secondly as the part of the traverse, obviously. So you can see it's T1 to T4, and then there's T4 to T1. And then we have the azimuth fixed between them. This page here shows you the adjusted azimuth and horizontal distance and the relative standard deviation at 95% confidence level. If you look at the distance between T1 and T4, you can see that we are very close to meet the requirement. It's reduced from 13.5 millimeter to 4.7, which is a huge improvement. This section here shows the standard deviation of the coordinates, but if you can remember from the first couple of slides that I've explained the criteria for the bridge construction, I told you we need to meet a precision for the station or control survey station. I told you the precision of the control station should be plus or minus 2 millimeter confidence level, but if you look at the results here, you can see that our control stations, they did not meet the requirement. Still, we have the weakness at station 7, so you can see the error ellipse for this station is quite big, so it hasn't been improved. As you can see, we are very close to meet the requirement, and there are two further options within our resources that we can do. First, use the GNSS as a check on the longer line from T7 to T3. I will show you that line. Another option is to input a further traverse point to brace the system. So let's have a look at the first option. We take the longest diagonal and include the weakest station. In this case, I will include the T7, and then the longest diagonal would be to T3, and then I will take my GNSS receiver to the field and read 6 hours observation at each station. You can use the standard GPS option, but it's easier to use the manufacturer software, and basically they have the basic reduction to the distance vector. So I would recommend you use, like for example, if you're using the Trimble receiver, you use the TBC to get that vector, but you have this option also to use the standard, but I would say it's easier to use the manufacturer software. And then the final expected distance, a standard deviation, can be calculated using the instrument specification, in our case GNSS specification, which have been given to us. At the approximate distance of 2.1 kilometer, this gives us the plus or minus 5 millimeter. remember that you don't have this distance T3 to T7 as part of your output listing. If you want to get the adjusted distance, you have to calculate that based on the adjusted coordinates. If you also want to see that in the network plot, you have the option to go and select that from this option here, which is highlighted. You can click on that, and then you can type in the points from T3 to T7, and it shows the major and minor axis for ellipse, as well as the azimuth and distance that you have between them. So let's have a look at the listing output. If you really want to have the T7 to T3 in your output, you can use the trick we had before. If you can remember from the previous slide, I just taught you this one, which you put the distance from T7 to T3. You say that measure this distance to get the accuracy of plus and minus 5 millimeter in this case. So if you put this line or add this line to your data file, then line T3 to T7 is going to come in your output listing. So what I want you to see is, if you compare the value with the previous scenario, there is an improvement in the precision, especially for T7. If you look at the T7 accuracy, it has been improved by 1 mil, but the overall changes are very small, so it didn't really help us too much. That's why this scenario is out, so we try to consider the second option we had. The second option was we add 1 point. In this example, we can place the point Tx, I can call it, in the north of the bridge line, just west side of the T3, and then this allow us to measure to observation of T2, T3, T4, and T6. Now we can simulate this scenario by adding this point to the data file, and then we measure the angles and distance from this Tx to the above station, and then we probably add extra angle from T3 to Tx. Of course, we must create a new station Tx first, and then we can add those observations as part of the traverse. Let's have a look at the data file. So if I'm adding station Tx as is shown here, and then I'm adding those measurements to the previous traverse I've had, like I'm having extra reading of the angles and distance for these 4 stations, and I've considered T3, T2 to Tx is only angle reading, not angle and distances. Then it will come with different results, obviously, but you must say, hey Zoro, hang on, I know we can change lots of things and we can get different results, but I can't keep it in my mind. What we can do is, obviously we can create the table like this, and every time you're doing any options or changing something, you will write down the mean difference of your initial model. You can create a table like that, and for each of those scenarios from A to F, you can write down the difference between the mean difference between the first model you had and each of those scenarios, and then you can work it out how much improvement you had. So this is the mean of the standard deviation basically. So if I'm doing that, we can see from this table that if we assume that geometry is reasonable, so I'm not changing the geometry, then precision of the coordinates has been improved from model A to B increasingly, and then this one to this one, and this one to this one. So there was a huge improvement if I'm reading the so I haven't put anything for this one because I want to consider different scenario, because this one is out. We couldn't meet the criteria for the bridge control, so we are considering different scenario. So The second scenario is we are same as the first scenario, but we are reading two sets of angles and distance measurement, which has improved our difference to be up to 4 means. But you can see if you add this one, still there's a huge improvement. Like scenario C, we had T1 to T4 to meet the 2.2 millimeter standard deviation. The best way to analyze your results is you get the mean difference of a standard deviation of your different scenarios to the first model you've created. I didn't consider the first model because we obviously couldn't meet the criteria, so it's out. We are trying to have the different options, so there's no difference here. I can't really put 0 because I've considered the difference of each scenario to scenario A. Good. So that's why it's nil or not provided. So the second scenario, if you can remember, we read two sets of angle and distances, so it has been improved to by 3 mil. In this case 3.5, and this one is 2 mil, 3.5, and 2 mil, which is very good for easting and nosing. So now the effective way to do the analysis and comparison is we create a table and then you calculate the mean difference of each model to each scenario. The effective way to do the comparison is you create a table similar to this table and then you calculate the mean difference to model A in millimeter, obviously. Good. So I'm calculating the difference between each of these scenarios and model A, which was the first model we created in the local grid. And also I'm calculating the mean difference to the previous model. How much improvement I had from model B to C, model C to D, D to E, E to F, and obviously E to F, sorry, and D to E. So there's nothing written for the first line because there's no comparison. The first model was itself, so there's no comparison between model A and A. It's going to be 0. It's just itself. So you can see if from this table that if we assume that the geometry is reasonable, the biggest gain in precision of the coordinates has been from taking two sets of observation model B. You can see from this table that if we assume the geometry is reasonable, the biggest gain in precision of the coordinates has been from taking two sets of observation, for example, model B. So the biggest, if you look at the number and compare them to the rest of these, the biggest gain we had was from model B. So if we increase the number of observations from once to twice, so we are reading the distances twice, backward and forward, and 2 rounds of face left, face right for each angle, then you will see that this is the best option you have at the moment. Another two scenarios would be model G and H. But model G is basically a combination of model B and C. So we are reading two sets of angles and distances, and we are reading 12 distance for T1 to T4, as we explained before. Why we need to read 12? Because we want to meet the criteria for the bridge construction. This is our model G. You can see the improvement from this model to model A is easting and 4 millimeter for nosing. Obviously there is nil here because there is no previous one to be compared. And then the last scenario is same as model G, but in this case we are adding GNSS measurement and station TX. You can see from this model to from G to H, the improvement, it was very little, less than 1 mil, which is just insignificant. So this highlights that it's more efficient and less costly to increase the number of observations and running the analysis based on the model G, which gives us the accuracy we needed, and there is no extra need to get the GNSS observation or having the extra station. So the final result is presented here. If we choose model G, which is reading the distances and angles twice, and then we have the line T1 to T4 to measure 12 times, which has accuracy of 2.2 plus or minus at 68% confidence level. This is a line we've added and I've shown you before. If you combine those two together, the final result is gonna look like that. As you can see now, the coordinates, the station standard deviation, they all pretty much meet the required accuracy of plus and minus 2.5 millimeter, because this is at this 1 sigma is 68% confidence level. So they meet the criteria for the requirement for the bridge construction, except for the station T7, which is a little bit higher, but it's not really critical at this stage because these are all estimation obviously, and it's very close to meet the criteria. It's just half a mil off, which is not hugely critical. Obviously we can try to see whether we can get the exact 2.5 for that station. Let's have a look at the T1 to T4, which is our control line. You can see azimuth obviously is 0 because it's fixed, but also the distance for this control line can meet the accuracy requirement for the bridge control. If you look at the arrow ellipse, relative arrow ellipse, which is east-west and north-south, they are mostly falls within the requirement. Just in few cases it's not really what it should be. Example, the station 7 is a little bit larger than the requirement. In summary, taking into account of any possible errors which have not included here and allowing for checking for any blunder or systematic error, we can recommend a procedure for this kind of pre-analysis for any construction type project to be as first. We need to verify the total station prism or GNSS equipment. First of all, for total station, we have to make sure that we've done the EDM calibration and we verify our equipment against the regulation 13 baseline. We've talked about that in module 1. Once we've done that, we occupying PSM1 and then using two reference PSM P1 and P2, we can establish T1. The analysis showed that it should be within plus or minus 10 millimeter, which is required to match the precision for that point. And then we make sure that we place the recovery point, that if you kind of lose it for any reason, then you should be able to re-establish the T1. Then we occupying the station T1 and try to work it at the other station, where we want to put them, how we're going to cover all the area, make sure that you have the line of sight. And then once you've decided about your location, you can construct all the pillars, as I said, using the concrete well-driven type of structure, and make sure that it can settle and not being moved. Then we carry out the network observation. Remember, we have to choose 2 different days, preferably morning and afternoon, to have different correction, obviously for atmospheric. And then we traverse in opposite direction again to minimize any systematic and blunders error. And then once you are doing the traverse, remember you have to measure the T1 to T4 6 times. At each side, so it's going to be up to 12. And then a standard traverse observation to be 4 sets for each angle, face left, face right, and then 4 sets of distance to meet the requirement for the bridge setup. As we noted previously, we need to read the distance 4 times. Why you need to do the angles then? doesn't hurt. If you are there and you are measuring the forces of distance, you can easily measure the forces of angle. So as an extra check, you can always use GNSS observation and get the vector data between T7 and T2 or T7 and T4. We use T7 because it's the worst in terms of the precision. Usually it takes like 20, you can get the observation from 6 hours to 24 hours. Is basically up to you and the limitation you have. And then you can compare that with the adjusted one and see whether you have any blunder or gross errors. Next check you can do, remember you always can use the PSM 1 and 2 during your traverse. As a final check, you can always measure from P2 to T4. And also you can also have the recovery of T4 from P2, just in case that you lose T1 and you can't reestablish that. You still need to have the T4 recovery, and then from T4 you can obviously recover T1 if you want to. The other thing is, remember we did two-dimensional traverse, but in reality you cannot. You have to carry out a 3D adjustment. You have two options. We can either for 3D adjustment, obviously we have the zenith angle, and all of our distances need to be reduced to the horizontal distance. To compute the impact of the standard deviation of the zenith distances, you can use the table here on the right hand side. So remember we did a two-dimensional or 2D least square. Obviously the option is to carry a 3D adjustment, or if you don't want to do that, you can use the table here, and this number here on the right hand side for zenith angle, for different zenith angles, you can see it. You can add this number to your distance measurement, which are basically reducing from the slope distance to the horizontal distance. For example, if I have plus or minus 2 millimeter plus 3 ppm, I can add, if I'm measuring say to 85, I can add this number to my ppm. It can be 3.8 ppm, and account for that reduction from slope distance to horizontal distance. The final adjustment should combine the total station and GNSS observation, and the result obviously need to be checked carefully for any blunder or gross error, and then the chi-square test must pass, and F-test also can be done to compare post-prior distance uncertainty to manufacturer specification. This exercise hopefully should highlight how critical it is to follow the staged approach for any pre-analysis of control survey of construction work. We need to do the research and document the criteria obviously first, so you have to work it out what's the criteria to meet. Then we are carrying out the reconnaissance survey and note any available resources we have within your company obviously. Then you compile the data, and then you run an initial network pre-analysis. As a next step, we document our option, we test and compare different scenarios and options and find out what is the best model to use. We re-evaluate our assumption obviously to make sure that we haven't done anything wrong, and then once we've done that, we document our proposed procedure for implementation and maintenance of the network. In overall, this is the complex exercise to explain. Hopefully you watch this video, and if you have any problem with this lesson, or if you can't really understand one part of that, you will ask questions. You can email me, you can call me, or you can post in the forum, and I'm happy to explain more. Thank you.